Welcome back everyone to today's explainer. So if you're gearing up for Gujarat Technological University's Semester 7, we are going to decode exactly what you need to conquer subject code 3170916, Advanced Electric Drives. This is a 4-credit professional elective that basically bridges the gap between raw electrical power and highly sophisticated mechanical movement. Let's just dive right in.
Right off the bat, the course rationale states it plainly. Electric motor is an inevitable part of industries. And honestly, think about modern industrial automation for a second. We're talking manufacturing plants, robotics, electric vehicles, giant conveyor systems. Literally none of it moves without electric motors. They are the driving force of the modern industrial world. Mastering these machines isn't just some dry academic exercise, it's an absolutely critical skill for any engineer looking to work in automation or power systems today.
And that brings us to the core problem this whole course is trying to solve. Having a massive industrial motor is great, but raw, untamed power is completely useless if you can't control it. I mean, how do you ensure a robotic arm moves to the exact millimeter? Or how do you maintain the perfect speed on a massive manufacturing line when the physical load on it suddenly changes? The answer is precision control, and that's exactly what this syllabus is designed to teach you.
Here is our roadmap for this explainer. We'll cover 1. The need for precision. 2. Converters and controllers. 3. Mastering the motors. 4. Simulation and lab work. And finally, 5. Grading and course outcomes.
Starting off with Section 1, the need for precision, defining the drive.
So before taking this class, you needed the prerequisite of power electronics, and here is exactly why. An electric drive is not just a motor. It's an electric motor perfectly fused with a power electronic inverter and a smart control strategy. The ultimate goal here is to precisely govern speed and torque. Basically, you are taking those raw concepts from power electronics and applying them to manipulate actual, physical, mechanical motion.
Moving right along to Section 2, Converters and Controllers, the brains of the operation.
The syllabus tackles this so-called brain primarily in Modules 1 and 6. Module 1 gives you 10 intensive hours on power converters. You're going to dive into things like pulse width modulation, which is essentially rapidly flipping power on and off to control the motor, and space vector modulation. Then, jumping over to Module 6, you get 6 hours on DSPs, or digital signal processors. These act as the system's central nervous system to process incredibly fast, incredibly accurate motion commands.
Which brings us to Section 3, Mastering the Motors, the brawn. Now this is the absolute core of the syllabus, representing a massive 29 hours of lecture material across 4 specific types of machines. You'll spend 10 hours on induction motor drives, exploring direct torque control, and another 7 hours on synchronous motor drives. From there, you'll shift gears to more specialized tech, 6 hours on permanent magnet motors, specifically brushless DC and permanent magnet synchronous configurations, and finally, 6 hours on switched reluctance motor drives.
The narrative arc here is actually pretty clear. You start with the traditional stalwarts of the industry, your induction and synchronous AC drives, and contrast those with modern specialty drives like brushless DC and switched reluctance configurations. You'll be comparing their block diagrams and control mechanisms. Why? So that when you are the lead engineer on a factory floor, you know exactly which motor to choose for which real-world application.
All right, Section 4, Simulation and Lab Work, your proving ground.
Because let's face it, engineering isn't just about reading theory. The syllabus outlines suggestive experiments where you'll use software like MATLAB and PSIM to bridge the gap to real-world applications. You'll simulate things like regenerative braking, and that's the exact same technology modern EVs use to recharge their batteries while slowing down. You'll also get hands-on with major lab equipment, using digital oscilloscopes to visualize waveforms and PC-based controllers to manipulate the physical motors yourself.
Finally, Section 5, Grading and Course Outcomes, the Gauntlet.
Okay, now for the part every student actually wants to know. How are you getting evaluated? First, take a look at the cognitive demands based on the revised Bloom's taxonomy. Notice that remembrance, just simply memorizing facts, is only 15% of your grade. So rote memorization, yeah, it's not going to cut it here. A massive 60% of your evaluation relies on understanding and application. You have to actually comprehend how a drive works and apply that knowledge to solve complex problems, analyze systems, and evaluate performance.
Practically, this translates into a strict 150-mark structure. Your theory is out of 100 marks, 70 for the end semester exam and 30 for progressive assessment. Then, your practical skills are worth the remaining 50 marks. You have to treat the 30-mark Lab Viva and the 20-mark internal assessment with just as much respect as the textbook theory if you want to ace this.
This all builds into the 4 official course outcomes, which are equally weighted at 25% each. Just look at the action verbs here. Select, analyze. Select, evaluate. By the end of this course, you aren't just reciting facts. You're expected to make high-level engineering decisions to select components and evaluate the final performance of the system.
So, you now have the complete roadmap for advanced electric drives. You know that you are fusing power electronics with intelligent software to command massive industrial machines. You know exactly what the exams demand and where your focus needs to be. The tools, the software, the theories, they're all laid out right in front of you. The only question left is, when that motor powers up, are you ready to take control?